Hi everyone! Today, let's talk about section 12.1, Euler's method. Euler's method is the most basic procedure for finding the approximate solution of a first-order ordinary differential equations. So here we have the ordinary differential equation y prime equals f of xy. Okay, so y prime is the same as dy dx. And we have initial condition y of x0 equals y0 on the interval from x0 to xn, or we can say from a to b. Then we can find the step size h being xn minus x0 over n. Okay, so for example, if we want to draw a picture here, so we have a and here we have b. Here the differential equations actually give us a slope field. Okay, so a slope field, maybe it looks like that. This is the slope field. Okay, let's say here, this is x0, y0, and we want to get approximate a solution passing through this initial point, right? And just by looking at the picture, when we follow the slope field, it looks like our solution looks like this, right? But how do we actually get this solution? How to get approximate solution? What we do is we cut this interval from a to b into n subintervals. So a is like x0, and then we have x1, x2, b is like xn. Then what's the step size? The step size h is b minus a over n. And we call that the Taylor series approximation to the unknown function. We have y of x plus h equals y of x plus h times y prime of x plus h squared over 2 y double prime of eta, where eta is between x and x plus h. Okay? So in this case, Euler's method, this is our approximation. Okay, so this is our approximation. Okay, and the remainder is the error term. So Euler's method take y x plus h be yi plus 1, and y of x is yi, and y prime of x equals f of xi yi. And then we neglect the remainder. Then we get the approximate solution values y1, y2, yn at the points x1, x2, and xn. By computing this formula, yi plus 1 equals yi plus h f of xi yi. Okay, for I equal to 0, 1, 2, n minus 1. So geometric introduction. So Euler's method corresponds to using the line tangent to the solution y of x at x0 to find the values of y1. And then the approximation, so that is the approximation of y of x1. Okay, the equation of the tangent line with the slope y prime, okay, it equals f of x0, y0, and passing through the point x0, y0 is, this is the point slope form. Okay, so we call that a line. So a line with the slope n and passing through a point x0, y0. The line is y minus y0 equals m times x minus x0. Okay, and when we solve for y, then we get y equals y0 plus m. Actually, in this case, m is f of x0, y0. Okay, and that's why we get this formula. Okay, so let me draw a picture here. So we said this is the initial point. Suppose we have the slope field like this. Okay, what does the Euler's method do? So this is x0. Let's say this is x1. So we consider the tangent line passing through x0, y0, and then we use this as our approximated x1, y1. Okay, and then we imagine follow the slow field passing through this point, and then this is x2. We get this point is x2, y2. Okay, and then follow the tangent line at that point. Okay, and we get also a line segment. So we get a line segment. This is our approximation. So far, so good, everybody? Okay, so let's apply Euler's method to approximate the solution of an initial value problem over the indicated interval using n equals to 4 subintervals. So what we do here, first, we want to draw an interval. So this interval, x is from 0 to 4, and we want to cut it into 4 subintervals. And the midpoint is 2, and this is 1, this is 3. Oh, so you can see here the step size h equals 1. So that's the difference between each point. H is 1. And this is x0, x1, x2, x3, x4, right? We want to figure out y0, y1, y2, y3, y4. We want to figure out those. And what formula we use? So here, we want to use the formula that yi plus 1 equals yi plus xi plus 1 minus xi is h, and then f of xi yi. Well, in this case, we get xi squared plus yi squared. So far, so good, everybody? So this is our formula. Okay, so now let's plug in the different index. So y1, when we plug in I equal to 0, y1 is y0 plus h. In this case, h equals 1. And then we have x0 squared plus y0 squared. Y0, that is our initial value, that equals 1. Okay, now let's plug in 1 plus 1 times x0 is 0 squared plus 1 squared. So the answer is 2. y1 equals 2. So far, so good. Now we increase the index. y2 is then y1 plus 1 times x1 squared plus y1 squared. y1 is, see, now we're using those 2 points. y1 is 2. And then x1 squared, well, that's 1 squared. And then 2 squared. Well, 2 squared is 4. 4 plus 3 is 7. Okay, so we get y2 equals 7. Alright, so we use the previous 2 points to get the next y value. Okay, next one, y3 is then we're gonna use the 0.27. So this is y2. y2 is 7. And then plus 1 times x2 squared. So 2 squared plus 7 squared. Okay, if you're used to it, you don't need to write these again, because it's very similar, but just the index different. Okay, so we have 7. 2 squared is 4. 7 squared is 49. So we get 56 plus 4 is 60. Okay, so y3 equals 60. So far, so good, everybody? Okay, and then we keep going. y4 is then use the previous points. Y is going to be y3. The y value is 60 plus 1 times the x value is 3 squared plus the y value is 60 squared. Okay, this one we're going to need a calculator. Okay, calculator, 60 plus 3 squared is 9 plus 60 squared. Okay, so 3,669. Okay. So now we have figured out our answer. Okay. So this is the approximate solution of the initial value problem over the interval. Okay, so that's Euler's method. All right, let's continue. Next, we're going to talk about the Picard iterations. What is that? So we also given the first order ordinary differential equation. So we have y prime is a function of x and y. We have the initial value y of x0 equals y0. Now if we make a change of variables and assume that y is a function of x, we will get y prime of s equals f of s, y of s. Then we can integrate both sides, okay, and evaluate from x0 to x. Now, by fundamental theorem of calculus, the left-hand side, well, because integral and then y prime, antiderivative and derivative, they sort of cancel out. So it's just like y of x minus y of x0. Then, so because the left-hand side equals this, we can solve for y of x, well, which means, because this guy equals this, so we move the y of x0 on the right, and we get this formula. See, now we have solved y is a function of x. Okay, even though this looks like it is solved, but it isn't, because the function y is buried inside the integrand. To solve this, we use the following algorithm, known as the Picard iteration. So we construct a sequence ofyn's, the sequence of functions. Okay, and yn of x equals y0 plus the definite integral from x0 to x, f of s, comma, y sub I minus 1 of s ds. Okay, alright, so let's see how we calculate. Okay, so we have the same differential equation. Let's find the third Picard iterate. Okay, so we use the formula yn of x equals y0 plus integral from x0 to x, f of s, y I minus 1 s ds. So we use this formula. Okay, first step, what is x0? Well, x0 is 0, y0 is, in this case, y0 is 0. So far, so good? Okay, in our previous example, the y0 is 1, but here we pick a different initial point. Okay, so we get an origin. Then, we plug it in, y1 of x equals y0 is 0 plus integral from x0 is 0. From 0 to x, f of s, y I minus 1 is 0, so y value is 0. Okay, what is this guy? Well, f is x squared, so the first coordinate square plus the second coordinate square. See, we replace x by s, replace y by 0. Okay? ds. Well, that is just integral of s squared. That's s cubed over 3. Now we evaluate from 0 to x, which means we plug in x first, minus we plug in 0 is 0. So y1 of x equals x cubed over 3. So far, so good, everybody? Okay, I hope all of you can pause the video here and continue to find y2 and y3 of x. After you're done, please continue to play the video and check your work. Are you done? Okay, so y2 of x equals y0. y0 is 0 plus integral from 0 to x f of s. But here the y coordinate is going to be y1 of s. So y1 of s is s cubed over 3. What is that? Well, f of is like the x coordinates square plus the y coordinates square. So this is the same as s squared plus s to the, do we multiply 3 and 2 or we add 3 and 2? We multiply them, right? And 3 squared is 9. So the answer becomes s cubed over 3 plus s7 over 9 times 7 is 63. Evaluate from 0 to x. When we plug in x, we have x cubed over 3 and x to the 7 over 63. So far, so good, everybody? Okay, let's continue. So here we're only looking for y3 of x. So one more step we are done. So similarly, but here we plug in y2 of s, which is s cubed 3 plus s7 over 63. You can see when we go into more and more steps, it's become more and more complicated. S cubed over 3, S7 over 63, this guy square. Okay, in order to calculate, to integrate that, we need to FOIL it. So that's S cubed over 3 squared, that's S6 over 9. Plus 2 times s cubed over 3 and s7 over 63 plus s7 over 63 squared, which is s14 over 63 squared ds. Okay, what is that? Well, s squared integral is s cubed over 3. This is s7 over 9 times 7, 63. Okay, this one. This is s to the 10th. When we add 1, it becomes 2 times s to the 11. Right? And then over 3 times 63 over 11. That one, add 1 to the exponent divided by that exponent. Evaluate from 0 to x. So far, so good, everybody? Okay, so we just replace s by x. So x3 over 3 plus x7 over 63 to x to the 11 over... Well, you can also calculate what this is. Let's see. Calculator. 3 times 60... Oops. I mean to go here. So 3 times 63 times 11. Okay, that is 2079. And then we have 63 squared times 15. 59535. 59535. Okay, so this is our answer, y3 of x. Okay, we mark. You can see Euler's method will give values of the approximation yn. So it is a number. It gives us a set of points. okay, where the Picard iteration give us yn is a function of x. So that's the difference between Euler's method and the Picard iteration. Euler's method, we get a list of numbers. Those are the yi's values. And Picard iteration, we get a list of functions that are functions of x. Okay, good. So now let's continue. Let's look at the modified Euler's method. Okay, so our final view of the Euler's method is that based on the first term of a Taylor series approximation to the unknown function, right? We use, this is our approximation and this is the error. That's the Euler's method. This suggests that one way to obtain a better solution technique is to use more terms in the Taylor series for y. So in order to obtain higher order truncation error, for example, a second order Taylor method to use. So here we consider one more term, that is h squared over 2 times y double prime of x. And then this is our new error term. So compare with the old Euler's method, the modified Euler's method, we consider one more term, which involves the second derivative. Okay, let's use the modified Euler's method to approximate the solution of the following initial value problem using n equals 4, so intervals. So here we have the y prime. Okay, so we're good. We have the y prime, but we don't have a y double prime. What do we do? Well, we don't have a y double prime, but we can get it. Okay, how to get it? Well, this guy is y prime, right? So y prime equals xy. Y double prime, you just take the derivative of this guy, right? But we think of y as a function of x. So here we actually need product rule. So we have x prime y plus xy prime. Okay, this is product rule. So we think of y is a function of x. So we need a product rule here. So I don't know whether you took Calculus 3 before. So Calculus 3, we talk about partial derivatives. So let's say the partial derivatives with respect to x, we view the x is the variable, we view the y is like a constant. When we're looking for the partial derivative with respect to y, we consider y is a variable and x is the constant. But here is different. Here's different. We consider y is also a function of x. So when we take the derivative with respect to x, we need product rule because we have function of x, which is x times function of x, which is y of x. Okay, so x prime is 1, y prime is y prime, but we know what is y prime. Yeah, y prime is y prime is xy. So far, so good. So we get, this is y plus x squared y. This is the formula of y double prime, the second derivative. Now we're ready to write down the formula. So y1 equals y0. So just use this. Replace x plus h by y1, and y of x is y0, x is x0. Okay, then we have y0 plus h y prime of x0 y0 plus h squared over 2 y double prime of x0 y0. So far, so good. So this is the modified Euler's method. Okay, so here we still have the interval. This is from 1 to 5. We divide it into 4 subinterval. The midpoint is 3, and this is 2, this is 4. And you can see the h is also 1. Ooh, that's nice. Okay, so the This is x0, x1, x2, x3, x4. We're looking for y0, y1, y2, y3, y4. I strongly recommend you to draw this picture and write down the yi's at each steps. Okay, y0. What's y0? y0 is 1. Okay, then we use this point to find y1. What's y1? That is y0, which is 1, plus h is 1, y prime of x0, y0, y prime is xy, so we have, let's do one more steps. Okay, let's write down the formula again here. So this is x0, y0, this is h, oops, sorry, pressed the wrong button. Okay, y double prime is y0 plus x0 squared y0. Okay, now we can plug in. y0 is 1, h is 1, x0 is 1, y0 is 1. 1 over 2, 1 plus 1 squared 1. Oh, 1 plus 1 plus, well, 1 plus 1 is 2, 2 over 2 is 1. So the answer is just 3. Okay, next, we're going to use the points x1, y1 to get y2. So that's the y value of that point, which is 3 plus h is 1. And then the x, we plug in here. But with the x0, we replace x0 by x1, which is 2. We replace y0 by y1, which is 3. So we have 2 times 3 plus 1 over 2. Y value is 3, x value is 2, but squared times 3. Okay, what is that? So we get 3 plus 2 times 3 is 6. And this is 2 squares, 4. 4 times 3 is 12. 12 plus 3, 15. 15 over 2. So we get 9 plus, this is like 7.5. So 16.5 is y2. So far, so good, everybody? Okay, next, we're gonna continue and use x3, y3 to find, x2, y2 to find y3. So we have the y value, which is 16.5 plus, and then what happened? We have h is 1, x is 3, and this is 16.5 plus 1/2. Y is, let's see, here we have 16.5 plus x is 3 squared times 16.5. Okay. Now, because the last two steps is very easy to calculate, but now let me teach you a way how to calculate in a calculator, how to plug in your calculator too, and we can save some work for the future. Okay. So first, you're gonna do, you're gonna do 16.5. Enter. And then the next step, use answer. Okay, when you see the yi, use answer instead of putting in 16.5. Answer plus 1 times 3. So 3 times the answer. And then plus 1 over 2 times 16.5 is the answer. Plus 3 squared, and then times 16.5, which is the answer. See? And then close it. Enter. We get 148.5. Okay? So 148.5. And let me mark it down here. When you type in your calculator this number, you type in answer. Okay? So what is the good thing about it? Because now y4 is answer plus 1 times, well, here this is 148.5, but your x gonna change. So this 3, it changed to 4. But then next, we still have the answer, right? We still have the answer. Plus here, this is 4 squared and the answer. Is that okay, everybody? This is how we type in our calculator. Okay, so calculator, in your calculator, just go up to the previous line, but not yet. 3, change 3 to 4. Change 3 to 4. See? So the answer is 2004.75. So this is 2004.75. So this is the final answer. Okay, so you don't need to retype everything, especially when your function is complicated and its derivative and second derivative are complicated. Then we can use this answer function in our calculator. So far, so good, everybody? Okay, so that is the modified Euler's method. All right. Let's continue. So later on, we can use MATLAB to show you the difference between the Euler's method and the modified Euler's method. Okay, how accurate they are. Okay, example 4. For the given initial value problem, find the indicated Taylor approximating polynomials. Okay, so how do we find that? Well, what is the Taylor polynomial? Well, let me write down the Taylor polynomial. We have, let me change the color. So we have f of x equals f of a plus f prime of a x minus a plus f prime prime a over 2 x minus a squared plus dot dot dot. Okay, and in general we have k derivative over k factorial x minus a to the power of k. So far so good, everybody? Okay. So Taylor polynomial is the polynomial. It is powers of x, right? And let's see here. We want to find P3, right? P3 means we need to find the third derivative. Okay, so this is the first derivative, second derivative, well, product rule, x prime y plus xy prime. So far so good, everybody? And x prime is 1, so we have y plus xy prime. So far so good. We can also plug in y prime equals xy plus 1, or we can just leave it here. Okay, so let's continue. Y prime is gonna be the derivative of this guy, so we get y prime plus, well, next we're gonna have products, so we have product rule, so we have x prime y prime plus x y prime. Okay, and x prime is 1, so x y prime, so we get 2y prime plus xy prime. Okay, now our initial value, so a is like 0, so a is 0. Okay, and y of 0 equals 1. Now what is y prime of 0? Y prime of 0 is x is 0 times y of 0 plus 1, which is 1, right? That's y prime of 0. And y prime of 0 is, we're going to use this formula, y of 0, which is 1, plus 0 times y prime of 0. Y prime of 0 is 1. So the answer is also 1. Y triple prime of 0 is, we use this formula, 2 times y prime. Y prime is 1, plus x is 0 times y prime prime. Y prime prime is 1. So the answer is 2. See, when we're looking for those numbers, you can see it's okay to leave y prime or y prime prime there. You don't need to solve everything in terms of x and y, because when we're looking for the y prime, y double prime, y triple prime, we know these numbers. We know y prime and y double prime. We can just plug in to that formula. It can help us to save some work. Now, after we know those values, we're ready, because P3 of x is then y of 0 is 1, y prime of 0 is 1, and then we have x minus 0, okay? And the second derivative is 1 over 2, and then x squared. The third derivative is 2 over 3 factorial is the same as 3 times 2, and then x cubed. So the answer is 1 plus x plus x squared over 2 plus x cubed over 3. Okay, so this is a Taylor approximating polynomial. So be careful, everybody. The Taylor approximating polynomial is different than the Picard polynomial. Okay, so we talk about the Picard iterations. It also gives us y is like a function of x. But in this case, you will see the function we get, even though they are all polynomials, but they are different functions. Okay, so be careful with that. Let's continue. So, next example. Let's change to orange color. Okay, so, you can see here, A is 1. Okay, so let's first figure out y prime prime. Derivative of ln of x is 1 over x. Derivative of e to the y, because of chain rule, is going to be e to the y times y prime. Right? It's okay to leave it like that. Y prime 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 is derivative of 1 over x is, this is like x to the minus 1, so it's minus 1 times x to the negative 2. That's the same as minus 1 over x squared. And then this guy is gonna be product rule. First guy prime times second guy plus first guy times second guy prime. Okay? E to the y prime is e to the y times y prime. And there's another copy of y prime. That's e to the y prime prime. So far, so good, everybody? Oh! I just realized we only need to find P2 instead of P3. Okay? But it's okay. You know what? After you get, let's say this is P3, P2 is just the first 3 terms of it. Just ignore the last term, then you can get it. Let's find P3. So far, so good? Okay. Let's start. So here A is 1. Y of 1 is 0. Y prime of 1, we plug in x is 1. We get 1 plus e to the 1 is e times y prime. Oh, sorry, I plugged in the wrong formula. Y prime is this guy. Ln of 1 plus e to the 1 is e. And ln of 1 is 0, so y prime is e. y double prime. Then we look at this formula. 1 over 1 plus e to the 1 times y prime. Y prime is e. Oh, the answer is 1 plus e squared. Oh, sorry. I think I make a mistake. Because we should plug in e to the y, but y of 1 is 0. So here, this is e to the 0. And e to the 0 is actually 1. And here is e to the 0, e to the 0, because that will be 1. So the answer is 2. Yeah, sometimes, yeah, this tricky parts. Okay, we should plug in y instead of x. Yeah, and we have to be careful with that. Okay, and y triple prime is we're gonna use this formula. Minus 1 over 1 is 1. E to the 0 is 1. Y prime is 1. 1 times 1. E to the 0 is 1. Y prime is 2. Let's see. With minus 1 plus 1 plus 2. Oh, the answer is 2. See? Oh, I mean, this is equal. Okay, let's continue. So we're ready because P3 of x is y1 of 0. So y of 1 equals 0 plus y prime is 1 times x. Y double prime 2 over 2 times x squared, and then y prime of 1 is 2 over 3 factorial x cubed. So that is, oh, I make another mistake. What is that? Can anyone find out that mistake? The formula a is 1, a is not 0. So it should be power series, it should be powers of x minus a. Okay? So here, let me use a different color to indicate, this is my mistake. It's very easy to make mistake. And actually, this is a common mistake. Okay? I'm glad that we all catch it, and now we can see it. So this is x minus 1 squared, and this is x minus 1 cubed. So the answer is x minus 1. 2 and 2 cancel, plus x minus 1 squared, plus 3 factorials, like 3 times 2, 2 get cancelled. So 1/3 x minus 1 cubed. Okay, so this is P3, and the P2 is just those terms. So this is P2 of x. So far, so good, everybody? Okay, so that is the Taylor approximating polynomials, and they're different than the Picard iterations. So for this same example, you can also try to calculate the Picard iteration, which is hard, because if you can remember what we did for the Picard iterations, we actually plug in the s, okay, into the f, and integrate it. Well, if the function has exponential function or logarithm function in general is so complicated and to calculate. Okay, so I would say the Taylor approximating polynomial is easier to compute. Next, MATLAB, yay! So example 5, apply the Euler's method to approximate the solution of the initial value problem over the indicated interval using n equals to 10 subintervals. So I strongly recommend you to redo this problem using n equals 4. Okay? It would be a good exercise. Then you can check your work using this MATLAB. Okay, so the syntax is bracket x comma y, bracket equals Euler, parentheses, f, okay, f is a function, okay, and t span is the interval. So we have the interval from 0 to 2, then you put the bracket 0 comma 2 there. and y0 is 1, n equals 10. We want to divide it into 10 subintervals. Okay, so this is how we input it, and then we get 10 points. Okay. We can also plot the curve. We can input plot x comma y semicolon grid on, and then this is what we get. Okay, so let me show you in Octave. Okay, so in Octave, here, do you mind I copy it, or do you want me to retype it? I can do it either way. Okay, so x bracket x comma y is Euler, and then we have the inline function x squared times y squared plus y minus e to the y. See, e to the y is exp of y. The interval is from 0 to 2, and initial value y value is 1. And then we have 10 subintervals, and we get 10 points. And if we want to plot the points, we can input plot x, y with grid on. Okay, see? We get this E. Okay, we get the graph. This small graph, I can make it bigger. And you know what? If we increase the number of subintervals, we will get a more smooth graphs. See, it becomes very, very smooth, right? Okay, let's continue. So apply the modified Euler's method to approximate the solution. So here we have the same thing, but when you input it, you had to put Euler 2, okay? And instead of one function, you also need to include y prime prime. So this is y prime. How do we find y prime prime? Well, this is product rule. First guy prime, x squared prime is 2x times second guy plus first guy times second guy prime. Second guy prime is 2. So 2y squared prime is 2y times y prime. And then here we get y prime. E to the y derivative is e to the y times y prime. And you can see all of those factors consist of the y prime. We can factor that out, and we know y prime equals, this is the right hand side. Okay, so we can plug in here. And so we input this, and you can see here the function y prime or y prime prime, it is a function of two variables, x and y. You will see those variables in it. Okay, and we can input this, we can copy it. So we also get 10 points. And let's see here. Okay, Octave. So you see, we also get 10 points. Let's look at the last number. Okay, so the last point, the y value is minus 1.181. If we do the Euler's method 100 steps, we get minus 1.577. Okay, and if we just do Euler's method with 10 steps, we get minus 1.02. Let's see which one is closer. Keep in mind, minus 1.02, and this is minus 1.18. That is minus 1.05778. Let's see here. Okay, so if we increase the steps, let's do 100. Oh, so we also get small numbers, and they're quite close. But if we want to be closer, probably we need to increase. Let's do 500. Ooh, okay. So minus 1.5978. And if we do just the Euler's method, let's do 500. And let's see. You can see they're also very close. So far so good, everybody. Okay, I also want to check our answer with you. Okay, so we did the example 1. We can use MATLAB to check our work. Let's do it, if you don't mind. Okay, so here, let me go back. And I strongly recommend you to check your work. Okay, if you're able to use MATLAB to check your work, please check your work. So here we're doing 4 steps. Interval 0 to 4. And our function x squared plus y squared. Okay. See? Do we have the same numbers? 2, 7, 60, 3, 6, 6, 9. Yes. You see, it match with our answers. Okay? And let's plot it. Plot it. Okay. So, oh, you see? Those are like straight lines. Okay, but if we increase the number of intervals, like let's do 50. It's so big. Because that number square, x squared and y squared is gonna get very, very big. Okay, so we get a so big number. Okay, so far so good. Okay, but we can do, let's say, 10 steps. Then we can grab it. Okay, let's see. Oh, probably because the numbers are also so big. Yeah, it's too big, so it's hard to plug it. Okay, but we can also do, we did a 4-step and a match with our numbers. Let's continue. So Picard iteration, we won't be able to check that because it's a function, it's not a number. Okay, it's a function of x, like list of functions. And let's check this example. So here we have the modified Euler. With the function is, let's see here, we have 4 steps. And y1 is 1, and then 1 to 5. 1 to 5. Okay, and then we have let's see, y prime prime. Okay, y prime prime is y plus x squared y. So y plus x squared times y. Okay, and the y prime is just x times y. Oh, sorry. I delete more stuff. Okay, fix that. I delete a lot of stuff in line. Okay, is that good now? Oh, where's my brackets? Okay, brackets. Okay, is it good now? Let's see, why I have this parentheses, and why do I have that? No. Okay, then now it should be good. Okay, you can see it actually matched with our answer as well. So far, so good, everybody? So now you can try your homework about Euler's method and modify Euler's method. And then you can use MATLAB to check your work. And also, know how to find the Picard iterations and the Taylor approximating polynomials, even though they are also polynomials or functions of x, but they're different things. So far, so good. Okay, when you have questions, feel free to ask me. Have a nice day. Bye.